Okay, so this is a step one mechanics question that I'm going to try here. Basically, you'll get these a lot. It's just, well, how to describe it? It's just like resolving forces and taking moments. That's really it, actually. There's nothing else in this question at all. No nice ideas, nothing. It's just funky taking moments and resolving forces, right? So don't be intimidated by mechanics, Let's jump into it. Okay, the diagram shows a uniform rectangular laminate of sides 2A, 2B. We see that. So it's leaning against this rough vertical wall. Okay, it's rough, and it's rough here as well. So there's going to be reactions. R2, let's call them R2 and R1, why not? And then there's going to be, well, I don't know, to be fair, some people use like normal N1, N2. To be honest, I should probably start doing that because N usually means normal. Then we would use F for friction, and we would also usually use R for something called the resultant, which is going to come up in this question. It could come up in this question. There is a way to do it by considering the resultant force, but I'm actually not going to do that. I'm going to do it a different way. So it's fine to call them R1 and R2 for now. Okay, I'll quickly describe what the hell I just meant. So if you have, say, like a particle, and there's a normal reaction, and it's in limiting equilibrium, right? So there's going to be friction like that as well. If that's the case, what we can do is we can find a nice expression for mu. So we can have we can put the forces like head to tail like this. And then we have this hypotenuse of a right angle triangle. So although this was n, this is mu n. What happens now is this angle here, if we call it lambda, we see that actually tan of lambda is mu. Okay, so that's pretty cool. That comes up in this question, so you might spot that and think of a nice way to use that. I've been thinking about this for about a day, and still the most elegant solution I found is the one I'm going to present to you. If we go over here, we see that this is a resultant force. You usually call it the I'm not sure what force you call it actually. It's like the it's just the combination of the reaction and friction. You can represent that as one force. It's usually just called the resultant. I think there's another name for it, but I don't really know. So that's interesting. You can find a nice expression for mu by considering that force. If some of you were wondering if that was what I meant when I said that. Anyway, let's get back to the question and actually do it. So keeping that in mind, I'm going to do it a different way, and you'll see what I mean as I go through it now. So rest against the rough vertical wall, blah blah blah. So it gives you a sentence. The plane is this just verifies to you that this two-dimensional slice of this problem is indeed accurate within the laws of physics and the limitations that we're making. It means that you can do what you normally would do. Right now, this looks like a two-dimensional rectangular problem to you, but actually don't forget that we're considering it is in 3 dimensions. So how is that lamina leaning against the plane? Is it leaning in such a way that it's okay to do all these resolving forces and everything that we're about to do? Well, that pink brackety sentence there is just like, yeah, it's okay to treat it as you normally would. I hope I'm making sense. I feel like in this video I'm not making as much sense as I did in the others, but whatever. Show that, okay, we're going to show that the center of mass, so that's the first thing we want to do. If we mark on the center of mass with, a coordinate like G, what we basically want to do is we want to find various distances from the center of mass to the wall or whatever. And eventually what we're going to do, I could show that, but again, I'm just going to read ahead a little bit and find out what else they want me to do. The coefficient of friction at the 2 points of contact are each mu, and friction is limiting on both contacts. So that's kind of interesting, right? Now that means we can mark on friction going this way, mu R1, friction going this way, mu R2. How did I know that was the correct way friction was going? Well, what you've got to do is imagine where the lamina wants to go. So this side wants to slip down and this side wants to slip right. So obviously friction is going to oppose that. Okay, so we want to show this weird equation. Okay, so that was the thing I was talking about earlier. Tan lambda is mu. So it suggests that if you write these forces as the resultant force of friction and reaction, the problem may be easy. But you know, I didn't do it that way, so I'm just going to show you my way. So we want to show this equation. This equation is basically linking the coefficient of friction, this angle, and the size of the lamina. Okay, so the one thing that strikes me as odd is there's no forces in this equation. It seems that this relationship holds when friction is limiting, no matter what the weight of the lamina is. Okay, and it doesn't matter what the reactions are, or whatever. It just shows that the coefficient of friction and the two lengths of the sides, they seem to dictate alpha. So alpha can be found explicitly from this equation if we know everything else. More than that, if we know alpha, we can find the coefficient of friction of both surfaces. So it's an incredibly nice way of linking all of these things. So basically, I want to derive that equation at some point. But notice throughout this problem, there's no mention of the weight. Okay? So when we have a problem where, again, I said this problem, we're just resolving forces and taking moments. So resolving and moments. That is the only two things that we're going to do in our calculations. What we need to do here is think about, well, how would I do those two things to get this? Okay, I'm going to need more than one equation. So, I mean, the first thing to do, I guess, would be to mark on the weight. But my idea was to take moments about the center of mass, because if you do this, you're ignoring the weight. And in fact, this is just my first try. Okay, I guess if you have a question like this, you just gotta try certain things and see what'll happen. I'm just going to redraw this diagram here a little bigger so we can have a clear meaning for everything that's going on. So this is our lamina. It's a two-dimensional lamina. And I'm going to take moments about this. So I'm going to draw the forces on in green. So R1, mu R1. This is going to be R2 and mu R2. All right. Now, I don't know how you guys take moments. My friend told me, Tom Hanna, he's the other, I guess, the other math mo that's starting this Hannibal with me. He told me when you're taking moments, what you want to do is treat it like I mean, I'll tell you the way I used to do it was pretty retarded compared to his way, to be honest. I used to say anti-clockwise moments equal clockwise moments. And that I'd list the anti-clockwise on this side, I'd list the clockwise on this side, and I'd get very confused. And he told me, come on, man, like, you're a mathematician, right? What you need to do is take the moments. Whatever moments are acting anti-clockwise, we know they're negative, like, because clockwise is negative because, you know, clockwise is negative when you're measuring an angle anyway. When you're a mathematician and you measure an angle, anti-clockwise is positive. He actually has a clock in his room, right? And it goes around the correct mathematical way. so it does like this, right? And it's pretty cool. I really want this clock. I suggest you get it. But this is a MathMost clock apparently because you know, anti-clockwise is positive. So what we're going to do when we take moments is that any moments that end up being anti-clockwise, we're just going to write them all on one side of the equation. All the moments will go on one side of the equation, and any anti-clockwise moments will be negative. Any anti-clockwise will be positive. Any clockwise will be negative. We're going to write all the moments on the left-hand side, and we're going to set 0 on the right-hand side, if that makes sense, right? One thing we need right now is the distances. Okay, notice I don't have that at all, so I'm going to label them, you know, because what might happen is they might cancel each other out. Remember, in STEP, I don't have to calculate things explicitly. Like, I don't really want to be doing that. So if this is D1, this is D2, this is D3, and D4. Like, why not? What else would I call them, you know? Okay, so what these are is these are just distances I've made up in order for me to put them in a moments equation. I guess I should also give the center of mass a name. Most people call it G, so yeah. Okay, so taking moments by G, what happens? Well, you'll see we actually end up getting 3 clockwise moments and 1 anti-clockwise moment. All right, so we have minus D1 times mu R2, okay, and then we have minus D2 times R2, okay, and then we have negative mu R1 D3, and then we have plus R1 D4. So that's what I get when I take moments. Okay, interesting equation. But I'll just, before I tidy that up a little bit, I want to bring your attention to, okay, so how are we going to resolve forces? So this is our first equation that we have derived, right? The second equation that we're going to derive, well, what are we going to do? I want to resolve forces, but again, I really don't want the weight considered. I really don't want to introduce that variable. So, you know, I'm trying to fiddle my way around that. And what I'm going to do is, well, I can resolve forces horizontally. And we see that actually a really nice equation pops out. Just simply mu R1 is R2, right? So I can just plug that into to equation 1 right there. I didn't mean to cross through that, but, you know, whatever. Shit happens, I guess. So we want to, okay, what am I going to do first of all? There's 3 minuses on a plus. Right, so I wanna get rid of all that stuff. I wanna make 3 pluses on a minus, just because it's a little easier. Okay, and then I'm gonna sub R2. Anytime I see an R2, I'm gonna sub that in for mu R1. So what's gonna happen is I'm gonna get mu squared D1 plus, and this is gonna be, oh sorry, there's an R1 here. But you see what's gonna happen is everything's going to be in terms of R1, so I can cancel R1, provided R1 is not equal to 0. But we can check that, like the reaction is not going to be 0, so that's fine. So when I say R2 is mu R1, I can just sub in mu R1 in all of these cases, and the R1s will go, and I'll be left with a quadratic in mu, and this is exactly what I'm going to get here. So I'm going to get D2 plus D3 mu minus, because that became a minus now, minus D4 is 0. So this is my quadratic equation for mu. Okay, cool stuff. Okay, now I guess all that's left to do, I mean, I guess this should be the relationship that I want to show. Like, that's just a contorted version of this inequality. I guess we're going to name it star, right? Yeah, that's kind of step notation. So let's name this equality thing relationship. Let's name this relationship star. So I guess what I have over here, that should be equivalent to star. That should be exact same thing, right? Because you can see that this is mu. It's in terms of mu, and in terms of d is just so there's no forces in this equation as well. All that I really need to do is be very careful when I calculate the distances. Okay, so I mean, if we go up here, we spot something nice, right? I mean, this is alpha. We know A goes up to here, and then A goes up to here, and we know this bit here is B, and this angle here is also alpha, right? Because you know you can use like angles, like alternate angles or whatever to do that. Now, what you're going to spot here is that in order to get D1, which was actually the first bit of the question, we want to find the distance from the center of mass to the wall. But now you know why you're doing that, rather than actually starting the question and just doing it because they're telling you to. Now you know why it's needed. Okay, so we're going to calculate D1. This is just a simple case of resolving angles directly. We see this is A, so we're going to go along A and then up B. So we can see clearly that that's just going to be A cos theta and then plus B sine theta. Okay, if you want a more in-depth explanation of that, what we're doing here is A theta B. Sorry, whoops. So did I say theta? I meant alpha, and then B. And what we want is, we want this blue line here, that distance. So this is clearly going to be a cos alpha, and this is going to be b sine alpha if you drew, like, you know, triangles. But you really shouldn't be at the stage where you're drawing right angle triangles. You should just know by resolving that this is what this is. You know, this is the projection of it, I guess, onto that line or whatever. So we can see that, yeah, the d1 is just, of course, a cos theta plus b sine, sorry, a cos alpha plus b sine alpha. That's what d1 is. Okay, we can find a similar expression for d3. But get this, right? What's d2? Right? You'll notice the d2 and d3, you should first of all spot that, okay, well, they're actually in the same direction, so they must relate to one another somehow. And in fact, they do. We see that the vertical part of that triangle is just actually 2a sine alpha. Similarly, the horizontal part of the triangle is just 2a cos alpha. And we actually spot an equation linking d4 with d1 and d2 with d3. It comes out straight away. We see that that simply okay, one thing I want to point out is that how do we know that d2 is actually acting above the center of mass? Right? Like if we project this over here, how do we know that this distance is above? You know, how do we know it doesn't come below the center of mass? And even if it did, would that affect anything? Well, the answer is no. I guess you gotta show your mathematical sixth sense to spot that, and just say, look, even if the reaction comes below, what's going to happen if the reaction comes below? I mean, we're assuming it acts above the center of mass. If it's below, what we're going to say is then d2 will have an opposite sign. Right, the sign will change because we've assumed it's positive. So if it turns out not to be, we actually have a negative distance. So in that case, it'll be an opposite sign. Okay, but that's okay because the moment will change as well. Okay, moment changes too. So if you think about that for a second, it makes sense because even if it's negative, even if we did it as negative, the sign of d2 kind of autocorrects the whole mass so that the moment ends up being in the correct direction regardless of whether d2 is actually above or below, which is kind of cool. Like, let's admit that it's kind of cool. So anyway, now that we've resolved that, not actually in moments resolved, but in another, like, kind of literal sense, we've resolved that slight bump that we came across there in a logical argument. But anyway, what we want to do is I need some more room to write down these expressions. But yeah, you see how d1 links to d4, d2 links to d3. We see that d2, let's go over here, d2 is going to be 2a sine alpha minus d3. We see also that d4 is going to be 2a cos alpha minus d1. All right, so that is interesting. Now what I'm going to do here is, do we need to calculate d3? We have d1. All right, we've already got d1. d1 was a cos alpha plus b sine alpha. So I'll just write all my distance equations here. It took me a while to get them, but you know, here they are. Okay, I mean, let's just think for a second. We could calculate d3. I mean, d3 is just by symmetry, straight away, d3 is just going to be a sine alpha plus b cos alpha. So how did I know that? Well, if you think about d1, the way we calculated d1 is we used alpha to calculate d1. So in order to calculate d2, it's going to be the exact same thing. Instead of using alpha, we're going to use this angle here, whatever that is. And of course, that turns out to be 90 minus alpha. So by plugging 90 minus alpha into this equation here, what we end up getting is, you know, the cos turns into sine turns into cos, because we're all familiar with the identities, I hope, that a cos of alpha is sine of, you know, I say 90, I'm so used to 90, you know, pi over 2 minus alpha. Okay, we see that that's true. And similarly, you know, sine of alpha is cos of pi over 2 minus alpha. So be sure you're aware of those identities. All right, so we have all those distances, but why was I reluctant to calculate d free? Well, when I did this question, first of all, I did calculate d free, but then it actually ends up canceling out, which is kind of really nice. Okay, notice that we have d2 plus d free. Well, what's d2 plus d free? Now, straight away from this equation, d2 plus d free is just 2a sine alpha. So we actually never needed to know the value of d free, right? So by plugging in d2 plus d free there is 2a sine alpha. What I'm going to do is I'm going to leave d1 as it is first of all. Then I'm going to go 2a sine alpha. And of course, what's d4? Well, d4 we said was 2a cos alpha minus d1. So we see we're going to have another d1 join the party over there. Okay, so what I'm going to get is mu squared plus 1 d1 plus, what's the best way to do this? I don't even know if there is one. I guess just write it. I don't know what to do yet, so I'm just going to write it as it is. I could factor it like a 2 and an a, but let's leave it as that. First of all, because I'm not really sure what trigonometric identities I'm about to apply to this thing in order to get star. Alright, now one thing that's important is that in our star, the equation that they want us to show, we see, whoops, just start my pen. We see that mu is, of course, tan lambda. Now you should be kind of happy when you see this, right? So if mu is tan lambda, we're gonna shove a tan lambda over there. When you see this guy here, you know, you realize that this is actually tan squared plus 1. It's actually sec squared lambda, which is kind of nice. Now d1, I guess we're just gonna go ahead and sub d1 in for what it is: a cos alpha plus b sine alpha. And okay, yeah, I guess I could take these guys to the other side. This seems to make sense. So it's going to be 2a, so that's cos of alpha. And then notice we're taking away now. We're taking away mu sine alpha. Okay, I really don't know why I wrote that bit in green. No real reason. It's not any different from this. But yeah, I just like changing kind of frequently. So what is true now? Well, we have a sec squared and we have an a cos and b sine and stuff. One thing, just keep checking back at star and being like, okay, what am I trying to get towards? And one thing that strikes out to you is that b and a are on both sides. Well, what I mean is b and a are opposite sides. So one side is purely in terms of b, one side is purely in terms of a. So in order to work our way towards that, I suppose now we should go, okay, well, I mean, there's only one b in this equation. So let's try and make b sine alpha the subject, because that's just what it was in star. So what seems to make sense to me now is multiplying both sides by cos squared lambda in order to get rid of the sec. Okay. So what we're going to have is a cos alpha plus b sine alpha is 2a, and there's just going to be a cos squared lambda. I'm going to leave it outside for the minute because again I'm not sure what to do. And yeah, I had a bit of a mental fart here. I really should have just plugged in tan lambda straight away. Don't know why I didn't do that. And there we have that. Okay, so I guess now what we want to do is subtract a cos alpha from both sides. Seems to make sense, right? So we end up getting b sine alpha is, we're still not 100% sure how this is going to plan out, but you know, 2a, well again now we actually can't factor out a 2a. We can't even factor out the cos squared, so this is going to change things a little bit. Change the game plan. Okay, I want an a on the outside. Okay, and actually No. Let's just leave the A outside first. I want to do it slowly just to make sure I don't make any mistakes. Okay, so what do we have? We have 2 cos squared lambda cos of alpha minus cos of alpha minus, and remember that cos squared is going to conjoin with a tan squared. So what's cos squared times tan squared? One cos times tan will be sine. The other will be just sine cos. Let's keep the green pen here. So, and the 2 will come in as well. So we're going to have a 2 sine lambda cos lambda. Hey, that looks familiar, guys, right? We all know what that means. Sine alpha. Wow. Okay, so now what we're going to do is, so we have b sine alpha on that side. Okay, cool. We're aware of that. We're aware of that b sine alpha. Now this is equal to a times what? Well, this both has a cos alpha, so let's factor that out. And we get something familiar again. And over here we know that this is actually sine of 2 lambda times sine of alpha. And now what? Well, we know that this is cos of 2 lambda. Cos of 2 lambda cos of alpha minus sine of 2 lambda sine of alpha. Well, what is that? Again, I mean, I would, because I did the question already, I kind of know where I'm going, but while I was doing it, in order to derive this identity, I had to frequently track back and forward. I kept looking at star like, oh my god, what am I doing? What do I want? What you can do is you can take star and expand it out. But we you know, you might spot that this is simply this, right? I mean, that's cool. And this is star, so we're there, right? We see that this is just, you know, the cos double angle formula, which is great. You know, this is just great news that we got there after all that mess. Oh my god, yay. You know, just like that feeling of utter joy is just unbelievable when you actually get the answer out. Okay, so we're done. If anyone knows any better ways to do that other than slugging for the algebra, do let me know in the comments, because it took a while. You know, I will investigate how to do that with the free forces. Oh yeah, there's one more bit, but it's not hard. Okay, show that if the lambda is a square, then we can evaluate lambda explicitly. So what does lambda being a square actually imply? Thinking about it for hopefully not too long will give you the answer that if a lambda is a square, then b is a. Okay, so a is b, so we can just cancel a and b, right? And we're left with a strange equation. Well, it's just here, you know, sine alpha is this. Okay, so the proper way to solve one of these is to take sine and apply the identity. Sine of alpha is cos of pi over 2 minus alpha, as I talked about earlier. So we're just going to apply that, or we get cos of pi over 2 minus alpha is actually equal to cos of 2 lambda plus alpha. Now we've got to be really, really careful here. We can like remove the cos from both sides, but of course we can only do that if the angles here are, you know, in the same quadrant, you could say. If you think about the cos curve for a second, you'll realize that okay, if both angles are, I guess, between 0 and 90, it's okay to do, right? Basically, a lot of careful thought will go into this. If both angles are acute, then it'll be okay to just say this. Okay, and then of course we can get the result that we want. But okay, like, how do we know that this is okay? You know, this is something I actually struggle with still to this day. It's just a little bit tricky, really, isn't it? Just consider the sine and the angles, right? we know that alpha is between 0 and pi over 2. So clearly this side is between 0 and pi over 2. Clearly that's how it's limited. Okay. But what about the other side? Well, I guess that it does also follow that. Like if you think about it for a second, cos of an angle between yeah, this is it. Okay, so if you imagine cos of an angle between 0 and pi over 2, we see it's strictly positive, right? It's between 0 and 1. So in order for that to be equal, I guess that this angle has to be between 0 and 1. And the only way for it to do that is either it's it's between 0 and pi over 2, or it's between 3 pi over 2 and 2 pi. And we know that's not the case here. Okay, like clearly that's not the case because we have 3 acute angles. So what must happen is, of course, there's 3 acute angles theoretically without any, without any like barriers on them. Could range anywhere from 0 to 3 pi over 2, 3 times 90 because they're all acute. They could all lie in that range, but they could also lie in a very much smaller range, and that is usually the case. Like they could be bounded upwards by like pi over 2 or something. We don't really know any information about those 3 angles, so the range is very wide. But of course, we know that they can't be any bigger than 3 pi over 2. So basically, what I'm saying is this is acute. Does that make sense? Like if this equation holds, this angle has to be acute. Okay, we're only considering angles between 0 and 2 pi here. I'm trying to convince myself of this argument as I'm trying to say it to you guys, but I think it's pretty sound. That angle cannot be, yeah, I mean that angle has to be acute just by the fact that this equation holds. That angle has to be acute. So that seems to make sense to me. So therefore, if the angle is acute, we can remove the cos and we're fine because we know that the angle's in the same quadrant, right? So we can take inverse cos, it's fine. And then we're done. Okay, so I don't know how many marks that last bit would be worth actually. I don't know, I'd say maybe quite more than you would think, maybe about 5 or 6. Just depending on the rigor of your logical explanation. I guess like a lot of marks would be for finishing off step questions rather than just laughing at an answer and be like, oh, here you go, it's that, and then not really thinking in depth about all the possible various cases and stuff. So the fact that we took our time to explain that, and also the fact that we said that D2 was, I guess it's really a vector, isn't it? Like it's not just a distance, so the distance could be negative or whatever. But yeah, I mean, that was my way of doing this question. And it was pretty tricky, I'm not gonna lie. It was a pretty tricky question. In an earlier video, I said question 9 was usually easier. I think it is. Like the only reason I find this tricky is because I haven't done a question like this in ages. But I mean, if this is your kind of thing, you're probably even better at it than me by now. You're probably watching this video being like, oh, look at this schmuck, haha, But basically, I'll do a few more on resolving and taking moments, and you start to build up a picture in your head about what you need to do. So in terms of the hard bits of this question, like it wasn't the actual question that was hard. It was all the wee fiddly things like spotting exactly what to do, but also like seeing a lot of relationships. Well, I guess. Well, I don't know. I mean, if we think about it, it's not really that tricky, is it? I mean, what I really think is how tricky it is depends on how tricky you think it is. Right? If you go in and with a good psychological attitude, you'll come out with a good question. If you go in thinking it's tricky, it often tends to be tricky. He who thinks he can, he who thinks he can't are both right. So I'm going to finish this question with a kind of a philosophically strange argument that in order to get good at STEP, you need to believe that you're good at STEP. You need to believe that you can do it. You need to keep repeating to yourself, it's easy, right? Because if you don't do that, then, what's the other option? You're going to say it's very difficult and it'll self-perpetuate. So don't do that. Even if it's really fucking hard, like fake it till you make it, okay? So, yeah, that's that. I hope this video was vaguely helpful again. So thanks, guys. Thanks for watching.